Dear students of class 12, my name is V. Ravishankar. I am a physics teacher in IIT Delhi, and what I am going to do in the next 7 or 8 lectures, we do not know how many, is to discuss the topics on the so called modern physics in your 12th standard physics course. So, essentially they will be chapters 11 to 13, and what we are going to cover are photoelectric effect, the de Broglie waves, Bohr model of the atom, and nuclear physics. This course is qualitatively different from whatever you have studied in your 11th and 12th standard. You covered a whole lot of courses. For example, you studied mechanics, both statics and dynamics. Then you studied electricity and magnetism, thermodynamics, optics, properties of matter. In all these topics, you were trained to solve a large number of problems, and some of them are quite intricate. This course is not exactly like that, because the mathematics that we are going to use is quite elementary. In fact, much more elementary than what you would use in, let us say, electromagnetism or mechanics or gravitation for that matter, rotational motion especially. But on the other hand, the concepts that we discuss are very, very deep. They are radical, so radical that at the beginning of the 20th century, last century, when great physicists like Hertz, Einstein, Millikan, name goes on and on, Lorentz, Bohr, Heisenberg, when these people encountered, they were completely startled. So, it does not mean that the subject is only conceptually difficult and mathematically easy. It is just that this particular course introduces to you the conceptual basis in a very simple way. But of course, after that, when you join for your graduation or post graduation in physics, you will start learning the mathematical aspects, the quantitative aspects, which actually is extraordinarily sophisticated. The other thing about the topics that we are going to study is that there are some fundamental issues on which great physicists even ponder about. For example, wave particle duality, what exactly does it mean? What exactly is the meaning of the uncertainty principle? What does one mean by measurement? These are the questions that we do not normally ponder about when we study classical mechanics. You were taught particle properties, you were taught wave properties, you did not have to worry. But here you do have to worry, because the same physical system can show or exhibit both particle nature and wave-like nature depending on the condition. So, there are lot of implications not only for physics, but also for metaphysics actually. Of course, we are not going to get into that. But the point that I am going to make here, or I am trying to make here, is that please do not take this lightly. In a certain sense, you can relax, because there will not be too much of mathematics. But in another sense, you have to be completely alert, because what we are going to discuss is really one of the most astounding achievements of humanity. We can very safely say that and proudly say that. So, with this brief introduction, it is actually good to announce our motto. What is the motto that we want to announce? We want to keep it simple, but we do not want to make it trivial, and this was very beautifully expressed by none other than the great Einstein, and you see that here in the next slide. So, it is good to announce what our motto is at this particular point, and what I am trying to say is that we are going to try to make things easy but not trivial, and this was very beautifully put by none other than the great Einstein, which you will see in the next slide. And if you look at this slide, he said, simplify as much as possible, but never oversimplify. Oversimplification gives rise to a feeling that you have understood something, or sometimes even everything, when actually it is not the case, and we shall try to follow this dictum. So, as I told you, this slide displays for you what are all the topics that I am going to cover. So, let me repeat so that it sort of gets fixed in your mind. The first topic that we are going to cover is photoelectric effect, and I am going to spend a lot of time discussing this effect, because not only do we have to write down the famous Einstein formula for the stopping potential or the ionization potential, we also have to describe the great experiments of Hertz and Mulliken very, very carefully, and also Lenard. I am going to spend a lot of time on that. And you should remember that Einstein got his Nobel Prize not for either his special theory of relativity or general theory of relativity, but for photoelectric effect. So, when you read photoelectric effect in your CBSE textbook or any other textbook, you may wonder, there is nothing much to do. Why is it that he was given a Nobel Prize? The answer to that came from Einstein himself. He said that creating special theory of relativity was a child's play comparing to obtaining an explanation, a proper description of the experimental results on photoelectric effect, because when it comes to relativity, he had the wisdom of 300 years of electromagnetic theory, Lorentz, Poincare and so forth, whereas when it came to photoelectric effect, he was charting his own course. So, that is something that we have to remember, and therefore, I am going to discuss the experiments very, very carefully and in great detail. So, when I speak of photoelectric effect, I am discussing the particle nature of light. Light is an electromagnetic wave. You people have solved many, many problems. Conversely, it was observed by de Broglie when he became aware of Bohr's work on quantization, that we can also ascribe a wave-like nature to the particles. So, in the first case, what was behaving like a wave classically started behaving like a particle in some context. In the second case, what was behaving like a particle in your cathode ray tube or whatever, when it goes to the atomic scale, it starts behaving like a wave. It starts showing wave-like property. And of course, a brilliant experimental verification came from the works of Davison and Germer, and we are going to discuss that. So, these two are two complementary aspects of the same, what we call as the quantum mechanical systems, and in the classical limit, one of them exhibits only wave-like nature and another exhibits only particle-like nature, but in the quantum limit, well, it depends on the situation. That is something that we are going to spend quite some time about. Next comes the nature of the atom. This of course is an extraordinarily important topic for us to study, because ever since the early dawn of intellect in humanity, people always wondered about what the ultimate constituents of matter can be. And of course, there were many, many theories. For example, in our own country, there is this school called the Vaisheshika school, right? They argued that everything is ultimately made up of atoms. Their propounder was a philosopher called Kanada. In a similar manner, there was a corresponding school in the Greek civilization, where Democritus said that everything is ultimately made up of atoms. Of course, there were counter theories where people believed that matter is actually continuous, we do not really need the atomic nature, and this discussion went on and on and on. For example, when you study electromagnetic theory, or let us say problems in moment of inertia, or problems involving rotational motion, rigid bodies, you assume that the density is a continuous function of space-time coordinates. Okay, if it is rigid, it is a function of only space. So, you treat them as continuous functions. You treat the charge density as a continuous function, whereas if you want to understand thermodynamics, you would have to employ the molecular hypothesis. So, sometimes it is convenient to treat it as a continuum, sometimes you actually need the molecular hypothesis to understand equilibrium phenomena. So, this is a fundamental problem to be actually decided by experiments and their interpretation. And when it comes to atoms, the primary unit of chemistry, let us say, the most important information, the most important insight came from Rutherford scattering, and who gave the planetary model of the atom. We are then going to argue that planetary model of the atom gives rise to a whole lot of problems. What are the problems that it is going to give rise to? Well, there is a problem of stability, there is a problem of why my electron will not fall off into the proton, so on and so forth. And in order to understand that, Bohr proposed actually his famous Bohr model, where he was able to quantize angular momentum, quantize energy levels, and he was able to describe atomic systems. So that is something that Bohr did. This is something that we will be studying at a great detail. So what I want to do at this particular juncture is to take a few minutes and recall to your memory whatever you have studied and point out what are the differences that we are going to see when we study the so-called atomic phenomena, the microscopic phenomena vis-a-vis whatever you have studied in your macroscopic phenomena, be it electrodynamics or be it the classical mechanics. So let us start with a few preliminaries, and it does not harm us to get an overview. By the way, I am not going to start the lectures today. I am only going to give you this kind of a broad overview and an introduction. The real course will start from the next lecture, when I will start discussing the great experiments on photoelectric effect. Okay. So let us start with the Newtonian mechanics, because you must have heard of the word quantum mechanics, and we want to see what the differences are. I am not in a position to tell you what all the differences are. I am going to mention some of them, and even what I mention falls into the realm of the so-called old quantum theory. They get much more sophisticated and refined later. So please do not think that whatever I have told you is the gospel truth. There is an element of truth, but there is also some amount of ambiguity in it. That is fine, because all of learning is learning, unlearning and relearning. That is the process that we go. So what we are saying is that in Newtonian mechanics, suppose you give me a particle, let us say of mass m, and it has an initial velocity v naught and an initial position r naught, and you give me a force. This force can depend on where the particle is located and the time. So you can imagine, for example, an electric field produced between two capacitor plates which are getting charged or discharged. Then to a large extent my electric field between the plates is uniform, but it is a function of time. Actually, if you take the edge effects into account, it will also be a function of the position. Let us do that. So what does Newton tell us? Newton tells us that if you give me the initial position and if you give me the initial momentum mv naught, and if you give me the force, then rest of it is a matter of detail. What does detail mean? I can tell you the position and momentum at all later times. All observables that we construct are actually functions of position and momentum, or maybe their derivatives, if you really want to look at something like a torque or whatever. Therefore, Newtonian world is what we call as deterministic. Everything is determined. So what do? If you consider the simplest example of one dimensional case, I will write m d squared x by dt squared is equal to, let us say, f of x comma t, then I integrate. You people have integrated. In fact, if my force is independent of time, that job becomes even easier. I will write m dy by dt, this is the general method, is equal to f of x. And what do I do on the right hand side? I will write it as m dv by dx, dx by dt is equal to f. So therefore, that means I can write this equation and I can start integrating this equation. So how am I going to integrate this equation? So I can write m v dv is equal to f dx. That is how I am going to write. I can integrate this. Remember, my f is a function of x. So let us say I integrate it from v naught to v. So I will put a prime here, and I will put an x naught to x prime x, and I will put an x prime here. The right hand side is an integral which you can evaluate. You have been taught in the calculus. So for notation sake, I will call x comma x naught. That is a standard method of calculus, and this is going to give me m v squared by 2 minus v naught squared by 2 is equal to I of x comma x naught. Now the next step is even simpler. I will transfer this to the right hand side, and then I will get an expression for y dv by dt, and I will integrate the right hand side with respect to time. Actually, I can show you that step. That is the procedure that we are going to employ. So let us say, for simplicity's sake, v naught is equal to 0. Then what am I going to get? I am going to get v squared is equal to 2 by m I into x, x naught. Otherwise, I will have to write the other term. Therefore, my v is given by square root of 2 by m I of x comma x naught, and this is nothing but dx by dt. So we employ the same procedure and we write dx over root 2 by m into I is equal to dt. Integrate the left hand side, integrate the right hand side. You get a function of x, you invert it, then you can write x as a function of time. In fact, you can repeat this for your harmonic oscillator problem, for instance, and you will immediately find out what the solution is. So in other words, Newtonian mechanics is completely deterministic, number one. Number two, if I go back to the original slide, and if you look at m, v naught and r naught, there is no restriction on what your velocity can be and what your position can be. There is absolutely no restriction. That means you can specify your initial condition in any way you want with any degree of precision, and then Newtonian mechanics will take over and it will give you the position, velocity, acceleration, angular momentum, whatever you want at all later times. And therefore, what we have is a completely deterministic system. And if you have good mathematical skills, and if you have a powerful computer and you know how to write down your program, then there is no problem at all. What happens is that you should be able to solve everything. That is how people were able to work out, for example, the planetary dynamics, perturbation because of various planets, so on and so forth. Now just to give you a flavor of how quantum mechanics is going to be different. So as I told you, this is some kind of a general overall view. Let us take the example of gravitational force. So what do you have? Your F is given by g m by r squared. That is what you have. And let us say that your body is sitting in a circular orbit. These are the problems to solve. The earth going around the sun in a circular orbit, a satellite going around the earth in a circular orbit, moon is in a roughly circular orbit. These are the problems, geostationary orbits. If you want to do that, you will write mv squared by r. That is what you are going to write. Of course, this mass goes away, and when you study your gravitational phenomena, you will study the importance of cancelling mass on both the sides in a great detail. This r goes away and you get a beautiful expression, v squared is equal to gm by r. Now you see there is a free parameter r here. If you give me r, then v squared gets fixed, and if the v squared gets fixed, then of course its kinetic energy is fixed. But the important point is that this r is a continuous parameter. And you can change it at will. So what I would recommend to you people, all of you students, is to go back, open up your YouTube and look at how India was able to send its probe to Mars, the famous Mangalyaan. So what did they do? They first launched it into an orbit very close to the earth. Then there were these slingshots, is that right? There were these slingshots which kept on changing the orbit. That means when you are changing the orbit, this r is changing. Of course, there are other things that change because there is also a question of angular momentum, because in general the orbit is elliptical, but they were able to change it continuously. So if I am to show it to you in a schematic manner, you first put it in this orbit, then give it a shot, then it goes like this. Okay, forget about this, in this elliptical orbit. Then you get another shot like this, then it enters an even larger orbit. Then you give it another shot somewhere here, let us say, then it escapes and it gets into the orbit of Mars and it goes. And here, where you want to put your satellite, this is my Earth and this is satellite, right? It's entirely under your control. So this is like a caricature of Mangalyaan. So look at that. And they did it in a very, very controlled way because everything obeyed Newtonian mechanics. But when you study Bohr atom, Bohr will say, no, no, no. You cannot simply write the equation Gmm by r square is equal to mv squared by r, because this r cannot be arbitrary. Is that okay? This r cannot be arbitrary. It should satisfy a very special condition. So what does that condition mean? It says that, for example, if a particle can be in this orbit, a particle can be in this orbit, but a particle cannot be in any of these orbits inside or any of the orbits between these two, and that is what is called as the quantization condition. That is why it is called as quantum mechanics. And all of you are familiar with the condition m v n r n is n h bar. That is what you are going to study, right? This is the orbital angular momentum. This orbital angular momentum cannot take any value that you can give. You should satisfy the condition that it is an integral multiple of h bar. H bar is your famous Planck's constant, h by 2 pi. H is usually called the Planck's constant and h by 2 pi is your h bar. And this Planck constant actually came from the photoelectric effect, and that is something that you are going to study in great detail depending on the experimental thing. However, in order to understand photoelectric effect, there are some things that we have to recall, and let me spend some time telling you what is it that you have to recall. So remember, you studied electrostatics, magnetism, and of course you study electromagnetism. I want to recall to your memory the salient features, the most important features. So what is it that we learned when it came to electricity and magnetism? That is very, very important. So all of you have solved, for example, the problem of RC circuit, and you have studied how energy flows into the electric field between two capacitors. So when you work out the energy, you write a beautiful equation, epsilon naught 2 by E squared is the energy density of the due to the electric field. So electric field is there. That is the most important role of a capacitor in modern day appliances. It puts charge and it stores energy, and you can use that energy anytime you want. And where does that get the energy from? Of course, it gets the energy from the battery or the cell to which you have connected. So let us not forget that it is not coming from nowhere. So you have your resistance, you have your capacitor, and then you have your charging thing, and then you put a switch. The minute you connect your switch, the current flows, the positive charges accumulate, and now the energy gets stored in between them. So electric field can store energy. In a similar manner, when you look at induction, for example, there is a corresponding magnetic energy which can be again harnessed, and that you write as, I hope I am writing the correct expression, V squared. This is the magnetic energy density. You people have studied this. So therefore, energy can be stored either as magnetic energy or as electrical energy, and it can be used. But then we have another law, the great law Faraday's law of induction. And what did he teach us? He taught us that time dependent electric field implies non-vanishing magnetic field. So how do I write that? So the change in the magnetic flux or the induced EMF is nothing but the change minus delta phi by delta t, which is the electric flux. Okay. time dependent electric field can actually produce a magnetic field. That is what we are going to write, and this is the magnetic flux. Okay? And again you are familiar with that problem, because if you start producing a time dependent field, then immediately you make use of this equation and find out how much energy is stored in the magnetic field. But even more importantly, what Faraday taught us was that since a time dependent electric field can produce a magnetic field, and in a similar manner Maxwell taught us a time dependent magnetic field can produce an electric field, what happens? My electric field energy can go to magnetic field energy, which I will denote it as EM, and vice versa. And the great insight that came from this, because of Maxwell, was electromagnetic waves. Electromagnetic waves, where the electric field acts as a source for the magnetic field and the magnetic field acts as a source for the electric field. That is what Maxwell said. And when you work out, you find that these electromagnetic waves travel with a speed of 1 over root epsilon naught mu naught. So all of you know what the values of epsilon naught mu naught are. Mu naught is 4 pi into 10 to the power of minus 7 Newton meter or whatever, seriously epsilon. But the most important thing is, when you substitute these values, you will get this great magic number 3 into 10 to the power of 8 meters per second. That is what you are going to get. Independent measurements of the speed of light by a lot of people, including Romer, who actually determined it by looking at the eclipses of Jupiter, shows that light also travels with the same speed. So, since it is extremely unlikely that there can be two important quantities with the dimension of light, namely the speed of light itself and 1 over root epsilon mu naught, Maxwell made the great conjecture that what we call light is nothing but one part of the electromagnetic wave spectrum. That is what he said. And indeed, that was very, very brilliantly verified by Hertz, and in our own country by the great man J.C. Bose, who was able to produce microwaves when he was working in Presidency College, and he was able to see all of them. In fact, he was able to see diffraction phenomena in interference in the microwave region for the first time, and today his portrait adorns the famous Hall of Fame, the great Hall of Fame of electrical engineers. So we can be very legitimately proud of that. That is what we have. Now I am telling you all these things because I want to lay the foundations for the importance of the photoelectric effect. And you people in your class 12, again, when you are preparing for your exam or when you are studying in your class, you know how to write down the expression for the electric field and the magnetic field. So let us do that. So the most important concept for you is that of a plane wave. Is that right? So what do? I say a particle has a frequency omega. This is of course the angular frequency, and has a wave vector k. We know what it is, right? So 2 pi by mod k is the wavelength. That is what I have. And k divided by mod k is the direction of propagation. Right? And omega is 2 pi nu, where nu is your frequency. So what do we have? Omega equal to Ck, or if you feel like, nu lambda equal to C, where C is 3 into 10 to the power of 8 meters per second. That is what you have studied. So once I establish this, I can write down my electric field. And what is the expression for my electric field? Well, let me write it down for a plane polarization. So I will write E naught, and let me assume that the propagation direction is along the z axis. So I will write E naught I cos omega t minus kz. This is something I want you to pay a great attention to. And all of you know how to immediately write down the expression for the magnetic field. We are obviously employing the SI units. My magnetic field will be B naught by C into J cos omega t minus k z. That is what you are going to get. So, what are we going to do now? What we are going to do now is to ask, if this electromagnetic wave is propagating, which is nothing but light, at a certain frequency omega and a certain wave number k, 2 pi by k is of course my lambda, where is the energy? After all, we are all the time speaking of solar energy nowadays, because it is clean energy. In fact, this cleanest form of energy was first employed by nature when photosynthesis was started by the plants, and we all live because of that. Because of photosynthesis, not only is energy harnessed, but we also get a lot of oxygen. So, you see, my energy is stored both in the electric field and the magnetic field, and I can write down my expression E squared plus B squared. I suppose there is some epsilon naught here and there is a B mu naught here, epsilon mod 2 1 over 2 mu naught or whatever. Is that okay? This is my energy density, this is where the energy stored is. And what is the important point that we have to notice here? The important point that we have to notice here is that my wave is oscillating. So, when you speak of an oscillation, you give me the amplitude, you give me the frequency, and you give me the propagation direction. And what this expression is telling me is that the energy carried by the wave is completely independent of what? The frequency. It is a function entirely of the amplitude. That is what it is saying. In other words, my omega or k, they do not contribute. They do not contribute to energy. That is the most important thing. That is also true of the oscillators. Therefore, in fact, this can be looked upon as a collection of oscillators. In other words, my omega or k only tells me how many times it is oscillating, but the real energy is actually in the amplitude. How many times you go from minus x to plus x or whatever, that is the information that is being given to you. So, it depends only on E and B, and this is something which is well known, because as you keep on increasing the intensity of light, for example, you have 50 watt bulb, 100 watt bulb, 500 watt bulb, then you are getting more and more energy. If you want to heat, you speak of rating of 1.3 kilowatt or whatever. Is that okay? That is what happens. So, this is a very well established fact and everything seems to be fine. However, what physicists observed was that this is all right if you are going to study electromagnetic theory only in isolation, but this gets into trouble when you look at what? When you are going to look at electromagnetic theory. So, let me write it fully. Electromagnetic theory plus thermodynamics. I cannot study anything, any fundamental theory in isolation. It has to be studied together with thermodynamics, because all real systems are at some finite temperature and all systems are interacting with their environment. That is an extraordinarily important thing. How did you produce light? You struck a match and you lit the candle, or you are going to heat something. For example, you may light a fire, set firewood on fire, or you may have embers, burning coals or whatever. All of them, their laws are governed by thermodynamics, and there are very, very important principles in thermodynamics. For example, the first law tells you that the total energy should be conserved, which is also there. But equally important, which you study in your kinetic theory of gases, is that at any temperature, each mode, this is very, very important. What is a mode? Degree of freedom carries an energy 3 by 2 kBT. Kb is your famous Boltzmann constant, right? It carries that unit of energy. In other words, thermodynamics asserts, and there is extraordinarily good experimental verification. In fact, we may keep on changing our laws of physics, but thermodynamics is going to be robust. Is that okay? that this equipartition is a very, very robust and a well established result. There is a very good experimental evidence, and this depends on the number of degrees of freedom. That is a very important thing. And at any given temperature, only at T equal to 0 can your energy be equal to 0. The minute you switch on the temperature, there will be oscillations. You will start interacting with whatever is there, and it will also acquire an energy, and each mode will get that. You students are thoroughly familiar with this because you have studied monoatomic gas, diatomic gas, and you know how to take, for example, the number of degrees of freedom into account. For example, if you have a diatomic gas, should you worry only about the vibrational states, or should you worry about the rotational states, so on and so forth. For example, for a monoatomic gas, so I should make a correction here. I am very sorry about that. Let me come back here. At any temperature, each mode gets not 3 by 2 degrees, but half kBT. So not 3 by 2, but half kBT units of energy. That is what it is. So if I come back to monoatomic gas, gases are sitting in 3 dimensions. So that will be 3 into half kBT. That is the energy carried by each molecule. That is the basis of the kinetic theory of gases. And if you have n molecules, you will multiply it by the n, and this will be the total energy of the system. And starting with this, you people know how to obtain, the famous gas laws like PV equal to RT, so on and so forth, by applying pressure. Either gas expands, or rather the gas compresses, so on and so forth. That is what we have. So you may say, so what? What does that have to do with my electromagnetic waves? So what we shall do, and this is the great experiment that we are going to look at. Imagine that you are going to confine your radiation in a pipe. It is closed here, and this is at some temperature. This cavity is at temperature, and there is electromagnetic wave. So it gets reflected at this point. So the wave is getting confined. You know that my k cannot be continuous. So it will be something like 2n pi. So k will be quantized. K will take discrete values. So k will be essentially kn will be proportional to n by L, where L is the length of the cavity. How do you get this? Length of the cavity. So you create a standing wave and you get that. Now you see my kn has become discrete. In fact, if you want a wave, there is a minimum kl which is given by 1 OL. It gets multiplied by 2 pi or whatever. You don't have to worry about that. So then you will have k1, k2, k3, etc., etc. And all these are discrete modes. These are the degrees of freedom. So even if you fix the intensity, there is nothing in physics which will tell me whether I should look at k1, whether I should look at k2 or k3. All these degrees of freedom are there. And how many are there? Well, I can draw a picture for you. So that is very much like a string. That is what I have. This is my fundamental mode, the so-called first harmonic. This corresponds to k1. Then I will write this. There is one node. Then I will write this. There is a second node, so on and so forth. There is no limit to the number of nodes. That means kn can take arbitrarily large values. So what is the statement that we are making? We are saying that if you confine electromagnetic wave, for example, within a certain region, let us say by putting reflectors or whatever, let us call it as a cavity. This is also very much like a vibrating string, if you feel like. Then it can take arbitrarily large values, means it has infinite degrees of freedom. It has an infinite number of degrees of freedom. An infinite number of degrees of freedom. Now what do? I couple my electromagnetic theory with thermodynamics. Electromagnetic theory plus thermodynamics. So what does electromagnetic theory tell me? It tells me my energy density is proportional to mod E squared, and this tells me it is proportional to number of modes, degrees of freedom, into half kT, and for all finite temperature, however small T may be, so long as it is not equal to 0, this is infinite and this is finite. So, as students, you people would have played a game where you suddenly get finite number is equal to infinite number, and immediately your friend tells you, or if your friend is committing a mistake, you tell this to a friend that you are doing something illegal. You are looking at something like 0 by 0 which is not well defined, and that is why you are getting that. You have no business to do that because 0 by 0 is not defined. In a similar manner here, the problem that we are getting is not because of mathematical problems, but there is a deep physical problem. This tells me there must be a finite energy density, this tells me there is an infinite energy density, and people actually performed very, very careful experiments, and what is it that they found? What they found was that actually the predictions depending on energy depending on the E squared, or the predictions depending on this half kT, was not going to work out the way we are looking at it. What it required was quantization. That is, you do not associate energy with the amplitude, but you associate energy with the frequency. Of course, you also associate it with the amplitude in a very sophisticated way, and I will come to that later when I discuss Einstein's explanation for the photoelectric effect. But you see, when I am speaking of photoelectric effect, I am not thinking of a small correction. It is not, these are all great achievements. For example, the discovery of the planet Uranus is a great achievement. But here we are looking at a deep contradiction in physics, deep paradox, deep problem in physics, and this is a kind of thing which gets shown up, which actually gets displayed when we look at a phenomenon like photoelectric effect or a Compton scattering or black body radiation. Therefore, what Einstein's photoelectric effect did was to actually resolve this particular problem. That is something that we have to know. And the beauty of this is that once it was resolved, this idea of Planck constant, Planck gave that constant for in order to explain this. Einstein used it very intelligently to understand photoelectric effect, and later Bohr put it into even greater use and a fantastic use by applying it to the atom, and he actually resolved the problem of the so-called stability. When I am using the word that he resolved the problem, that of course is in a very, very qualitative way. You would have to study quantum mechanics at great depth and in great detail, is it okay? But still you should be able to actually understand at least qualitatively whatever is happening. So, if I come back to my slide, whatever I am showing you, I am going to discuss after the photoelectric effect, Rutherford scattering, planetary model of the atom, and the Bohr model, is that okay? Where you have quantization of angular momentum, quantization of energy and atomic transition and so on and so forth. And after that, we are going to look at the interior of the atom. So, that is the beauty. Initially, Rutherford bombarded the gold foil with alpha particles, and he showed that most of the atom is empty. A similar experiment was done by Hofstadter with electron beams, and he showed that we can actually resolve the structure of the nucleus. It is of the order of the size, its size is of the order of 10 to the power of minus 15 meters. That is what we are going to do. And there we are going to study the properties of the atomic nucleus, protons, neutrons, why are some nuclei stable, why are some nuclei unstable. We are going to study the famous alpha, beta, gamma decays, fission and fusion. After studying fusion, I am going to give you an idea actually of how we can understand the fact that sun has been able to produce such an enormous energy for the billions of years, and it will continue to live for a few billion years. We are going to discuss that. And then of course, there is an important part of nuclear fission and fusion reactors. I am not going to spend too much time on that because there is not much to discuss except some matter of detail. I may just hint at that, and that should be essentially the course which is contained between chapters 11 and 13. So, we are not going to hurry up, we are going to take our time and we are going to study them. For those of you who feel that, okay, this is all there in some exotic nature, somewhere deep subatomic physics, why do I need quantum mechanics at all? What is the role of, Planck's constant or black body radiation or photoelectric effect for everyday life? You should understand that impact of quantum physics actually transcends everything. Is that okay? It is used everywhere today, and our latter part of the 20th century and the beginning of 21st century would be nowhere without quantum physics. So, let me remember, in your future chapter on semiconductor devices that you are going to study, is that okay? All the phenomena are based actually on quantum mechanics. Classical mechanics cannot explain, and all of modern technology is actually based on semiconductors and its various avatars. That is what we have. So, I have listed some of them to you in this slide. Your laptops and computers, smartphones, music recording systems, home appliances, or for that matter in medicine, your MRI, magnetic resonance imaging, PET scans, PET CT scans, etc., etc. All of them are based on developments in quantum physics. In other words, today we live in a world where quantum physics not only deepens our understanding into the microscopic world or the microcosmic world of atoms, nuclei and elementary particles, it also helps us to produce better and better instruments to make our life easier. Is that okay? So, that is something that we have to know. Within physics itself, it covers various phenomena in particle physics, in nuclear physics, in atomic and molecular physics, in condensed matter physics, and there is something even called as quantum thermodynamics or quantum statistical mechanics. It tells you how to understand cosmology, what the early universe was, what will be the fate of the universe, what was the beginning of the universe. Is that okay? All these are intricately tied, in fact completely tied to our understanding of quantum mechanics, and the beginning of quantum mechanics is something that we owe to what Planck and Einstein did. Historically, although Planck introduced the concept of Planck constant, he did not believe in the existence of photon. The real impetus, the real belief in the concept of the photon was actually from Einstein, who believed that it is really existing. It is not a mathematical construction, and many people thought that he was actually not being very sensible when he made that statement. Is that okay? You will get a glimpse of that when I discuss the photoelectric effect later, but that is how it is. Is that okay? So, that means all the developments that have taken place in the 20th century and taking in place in the 21st century owe a lot to Planck and Einstein. Of course, Einstein also gave us special relativity and general relativity. His 3 great papers were all published in 1905. That is why it is called Annulus Miraculus, year of miracles, as far as physics are concerned. Is that okay? He wrote special relativity, he wrote a paper on photoelectric effect, and he wrote a paper on Brownian motion, which established the molecular hypothesis of Boltzmann. So, they were fundamental papers, and you are going to study them slowly as you advance in your career in physics. But then, if at all we have to begin, we have to start with photoelectric effect, and that is what we are going to do. So, as I told you, it tells us about the physics of the interior of stars. For example, Helmholtz made a calculation and said that lifetime of the sun is not more than 21 million years, and it cannot live for more than another 5,000 years, whereas we know that sun has been there for at least 4.6 billion years. Okay, few million years ago there were actually dinosaurs and things like that, and age of the earth was a big problem. For example, Kelvin said that earth cannot be more than 100 million years old. Helmholtz said that sun cannot be more than 21 million years old. How can earth be older than the sun? That is first contradiction. And more importantly, we know that earth has been there for at least 4.5 billion years old. How do I know that? I know that because of the evidence coming from the fossils and rocks and so on and so forth. All these issues get resolved about the physics of the planetary system, physics of the earth, once we understand quantum phenomena and radioactivity, fusion and fission. That is something that you should know. Therefore, in other words, our scale is enormous, starting from let us say 10 to the power of minus 15 meters to probably 10 to the power of plus 15 or even more. Let me stop there. There are 30 orders of magnitude. There is no theory whose scope is as large as that, as deep as that, and that is something that we are going to study. So, to summarize whatever I have told you, we have studied laws of motion, we have studied thermodynamics, we have studied properties of matter, we have studied waves and oscillations, and we have actually studied that electrostatics and energy in electromagnetic field. magnetostatics and energy stored in magnetic field. I am summarizing whatever I worked out for you. Induction, displacement current, electromagnetic waves. We are going to make use of them. Is that okay? And once you brush all those things, read Faraday's law of induction, see how energy is stored in capacitors, how energy can be stored in inductors. Look at them. There is a beautiful analogy, between mass, spring constant, etc., of an oscillator and capacitance and inductor and resistance of in an electrical circuit. Resistance is like a frictional force, damping force. Was that okay? When you do that, if you come back from the next lecture onwards, lecture 2, we will start our photoelectric effect with basic preliminaries. So at this point, I am going to stop. So although it might appear to be some kind of a story, actually it is more than a story, it is more than a history, because I want you to go back, open your 11th and 12th standard books, read your chapters on gravitation, electricity, magnetism, mechanics and thermodynamics and optics, where you assumed that light is a ray. You did not even use the fact that it was a wave. Is that okay? Assimilate all that, remember that, and you come, then you will see how radical photoelectric effect, how radical a theory that photoelectric effect gave rise to, and that we will take up in the next lecture. Okay, goodbye.